I compressed the solenoid yet again, so now we're going to count the number of coils per meter as well. And it's so small, I think I'll go with, I'll try to count it within 20 centimeters and multiply it by 5. That's what I'll go for. So I'll do the best I can to count accurately here. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, 30, and I'm going to multiply that times 5, so we're talking 150 coils per meter. All right, and with that, I'm going to zero my sensor. Zeroed, and I'm going to make my initial measurement at 0, and I should get something close to 0 for my magnetic field. It's like it's biasing slightly negative, but we'll go with whatever we have. All right, and my statistics tell me it's kind of like what it was earlier, minus 0.0058. 0.0058. It's actually fairly negative, but that's after zeroing it, so that's the best I can do. So minus 0.0058. I'll take that actually minus 0.0059. I had to round up. And it's 0.0059 milliteslas at 0. Okay, here goes. I'm going to go all the way down here to 0.1. I'll work my way up. Save the best for last. Should have the strongest magnetic field at the end that we've seen yet today. Kind of leaves with a crescendo. All right, 0.1 amps. Here goes. Collect 0.1 amps. It's definitely more positive than it had been. Okay, at 0.1 amp, the mean is 0.013 milliteslas at 0.1. All right, let's go 0.2. .2 amps. Now collect and see what we get. Point 2 is, the mean is 0.031. Point 3. Okay, 0.3 looks like 0.046. Point 4. Point 4 is 0.066. Okay, now I'm at 0.5 amps. I already made the change. Let's see what the magnetic field is within the solenoid. It is 0.086. 0.086. All right, going to 0.6. It is 0.106. Point 7. Zero 0.122. Point 8. Point 0.138. Okay, it's already at 0.9. Press collect. And I'm at 0.158. Okay, the very last one. This should be the biggest magnetic field we've seen yet from the coil. One amp. Keep in mind, bigger magnetic field means stronger magnet. So if you want a strong electromagnet, you want more current, or you want more coils. Okay, here goes. We're at 1. Collect. Okay, and my mean is 0.176. So I'm going to put up a photo of all the data I've been collecting again. You'll see it in the next slide. Okay, now that you have all this data, you should have 30 data points that you could get off any of those photos or the videos, representing magnetic field measured from 3 different solenoids at 3 different spacings. So what are you going to do with it? Well, if you follow the lab procedure, it should be clear, but I just want to make sure that you really understand it. This is the equation that relates the current in amps to the magnetic field in Tesla. This is the N, that's the number of loops per meter. Okay, so it's either, I think, 58 or 92 or 150, whatever numbers I had given you earlier. That's what that N is. Then mu0 is something that you'll see in the physics lectures that we've talked about a little bit, called the permeability of free space. What your goal in this lab is to calculate this permeability of the free space based on the data that you collected. How would you do that? Well, for each of the 3 solenoids, each of the 3 stretches of the slinky that we used, you're going to be able to draw a graph of the magnetic field, and you got to make sure it's in Teslas. Remember, the values you were measuring were in milliteslas. So it's going to be at 1/1000th the value of what I wrote on the board, because those were milliteslas. So you're going to have to convert those to Teslas, graph them here, graph the current here. And I'm hoping, I'm more than hoping, I'm pretty sure, you're going to see a linear relationship between the magnetic field and the current for a given solenoid. If you plot all three on one graph, you'll have one that has a steeper slope, another one that has a middle slope, and then the final one has a smaller slope. So you should see, if you just do them all on one graph, you should see three different lines if you were to connect those points, one of which is going to be much steeper than the other two. What your goal is going to be is to calculate what value of the permeability of free space each of these graphs represents. How do you find that? What you can do is you can calculate what the slope is of each of these lines, and what should the slope be based upon this equation here. Well, if you think of this equation as the equation of a line, you could say that y is equal to mx plus b. B is probably close to 0. It should be 0. This means that at 0 current, you should have 0 magnetic field. We actually saw in a couple of the cases that we had a small magnetic field, perhaps even slightly negative, because of just the bias maybe of the Earth's magnetic field, even though we tried to zero it out. In any case, the slope is going to be the coefficient of this term which is x, which in our case is the current. So this value here, mu 0 n, should be the slope of each of these lines. So from that, you should be able to calculate mu 0 because you know what your n is. And you can compare your value of mu 0 to the known value and come up with a percentage error. And you get something reasonable. The value of mu 0 that you can compare is 4 pi times 10 to the minus 7. And the units of mu 0, which again is called the permeability of free space, are Tesla meters per ampere. Okay, so this is that special constant. It's kind of like epsilon 0, but for magnetic fields. Permeability of free space. Okay, good luck with that.